with that, I would just like to introduce our speaker today. We're very fortunate to have Francesca Parise, who's in our own Department of Electrical and Computer Engineering here. She joined as an assistant professor in July of 2020 after completing a postdoc at the Laboratory for Information and Decision Systems at MIT. Her PhD is from the Automatic Controls Laboratory at ETH Zurich, and she received that in 2016. And before that, she did her bachelor's and master's degree in Information and Automation Engineering from the University of Padova. She was recognized as an EECS Rising Star in 2017 and a recipient of Guglielmo Marin Award from Istituto Veneto di Scienza, Lettere et Arti, and an SNSF Early Postdoctoral Fellowship and an SNSF Postdoc Fellowship, as well as an ETH medal. So that's a lot. And so we're very, very excited to learn about what Francesca is up to with respect to analysis and interventions in large networks. And with that, I'll turn it over to Francesca.
Okay, thank you so much for the very kind introduction and for the invitation. It's really nice to talking to this audience. And so again, as mentioned, I'm going to present some of my recent results in the area of analysis and intervention for large network games. And just as a brief motivation, really the idea behind the work that I'm going to cover today comes from the observation that in many social and economic settings, we have that agents need to make strategic decisions, and they are not making this strategic decision in isolation, but they are making them while interacting with friends, colleagues, peers, or competitors. And there's many examples of this type of application. You can think about adoption of innovation and behavior, opinion formation and social learning, public good provision, or competition among firms. And really one thing that I want to stress is that being able to understand how agents make strategic decisions in these network environments is actually fundamental to understand how can we regulate this system and how can we design better policies. And this could be with the objective of maximizing the system performance or profits or overall welfare for the population. And I just have a couple of examples to kind of give you a sense of the type of question that arise in these type of settings. So as a first example, you can think in energy markets, one of the fundamental laws is that you always have to have this balance between energy supply and energy demand. And traditionally, it has been done by regulating the supply side, so regulating energy production. However, with the introduction of renewable energies, which are a little bit more unpredictable, people started suggesting that maybe actually we could start regulating the other side, so regulating the energy demand. And now you see why this brings in aspect about strategic behavior, because clearly energy consumption is not under the control of the energy authority, but actually depends on people's behavior. And so you have nice questions that arise, or how can we incentivize user to shift their energy consumption to period of time when that's beneficial for the grid, for example, by using different demand response pricing scheme. And again, the idea is that this now brings coupling between different agents' decision, because the time when I'm going to use my electricity is going to influence the price, which is going to influence decision of other people. And you can also find nice application in the area of marketing. For example, if you think about product adoption, an individual will adopt a product typically if enough of its friends have already done so and they kind of suggested that product to him or her. And so here, a very interesting question that arises in the area of marketing, for example, is if you are a company that's producing a product, how do you select individuals to seed, to individuals to which you may, for example, give the product for free, such that if they adopt your product, they will incentivize others to adopt as well, and that may maximize product adoption and therefore revenue. Or finally, similar question may arise also in a public policy domain. So if you think about network of individuals that in some way positively affect one another, so that increasing the welfare of one individual will increase actually a welfare of individuals that are connected to this agent, then a very important question, if you are want to intervene on this system but you have a limited budget, is how do I allocate this budget? Again, with the idea that I'm not just helping one agent, but I'm also helping around the neighborhood, and this has kind of positive spillover. And what I think is so challenging about this area that I've just described and this type of questions is that, again, you have this complex interaction between the human elements, so agents that make strategic decisions, for which we need like game theory in order to understand and how to model. And at the other side, you have the underlying infrastructure, which could be a technological infrastructure or could be interaction among individuals, like social interaction. And for that, you need kind of network theory in order to understand how to model these complex interactions. And then, of course, if you want to understand how to intervene on this system, you also need tools of control and optimization to understand how to maximize performances or maybe resilience of your system or overall welfare. And one area that's been very active in the last decade at the intersection basically of these different topics is the area of network games. And so this is kind of the mathematical framework that I'm going to use from now on in the talk to reason about this setting where we have strategic agents that make interaction over a network. And so from now on, I'm going to consider a population where I have capital N agents, again, that they are interacting over a network. And I'm going to represent this network with an adjacency matrix G, where the idea is that the element in position ij of this adjacency matrix is going to tell me what is the influence that a certain agent J has on agent I. And the objective of every agent here is to select a strategy xi, so make a decision among a feasible set of strategy, calligraphic xi, to minimize a certain cost function. And again, what makes this a game is the fact that this cost function is going to depend on the individual decision of the agent xi, but it's also going to depend on decision of others. And in fact, what makes this a network game is the fact that we can summarize the effect of others' decision on agent I through this local aggregate quantity zi of x, which really is just the average of action of other agents weighted by this parameter gij coming from your network. And again, as I mentioned here, we are a game theoretical setting, so the relevant outcome in this case is going to be encoded by the well-known concept of Nash equilibrium. And so just as a brief summary, a set of strategy x bar I is a Nash equilibrium if no agent has any interest in unilateral deviation, meaning that if all the other players are playing according to this strategy, then x bar I is the strategy that agent I should adopt to minimize its own cost function. And just to make sure that everybody's on the same page, I'm just going to cover very quickly two different examples of network games that has been studied a lot in the literature. So the first one is what is known as linear quadratic network game, where each agent actually needs to select an action xi, which is a positive, actually non-negative scalar. And this, you should think of it as like an activity level, how much effort this agent is putting on some activity, like for example, education or smoking. And the agent wants to select the best level of effort to minimize a cost function, which has two terms. So the first is like a cost associated to this effort, like devoting more time to this activity has a cost. And then the second one is actually the benefit that I get from participating into this activity, which in this simple case is proportional to the effort level according to what is known as the marginal return. And really what is interesting in this model is that this marginal return, so the benefit that I get from this activity, depends on what others are doing according to this zi value. Again, remember, zi is the local aggregate of what others are doing. And in particular, how much this matters for me is captured by this alpha parameter, which is sometimes called the peer effect parameter. And it's actually easy to see. If this parameter is greater than 0, then my marginal return is going to increase, right? The more other neighbors are taking part into this activity, the more I will have an incentive to do so. And these are so-called games of strategic complements. So education or smoking are classic example of that. Like the more my friends are spending time studying, the more I have an incentive to do so as well. But unfortunately, the same is true for smoking also. While in the other case, when alpha is negative, these are so-called games of strategic substitute. And then you see in that case, the marginal return decreases. So these are cases where the more my neighbors are taking part into the activity, the less I have an incentive to do so. And so there's some incentive to free ride maybe on effort of others. And one important feature of this model here, again, is that the action set is basically any level that is a non-negative scalar. So like I have a continuum possible of choices. However, we also have network games where the set of action is finite. So in the simplest case is a coordination game where actually agents can only choose between two different possible actions. So they can either choose 0 or 1, and these typically represent adopt a certain novation of behavior, buy a certain product or not. And the reason why these are called coordination game is that agents have an incentive to match with their neighbors in the underlying network, so that you see they will get a positive payoff only if the strategy matches to one of the neighbors. And note that importantly, they play this 2x2 game with each one of their neighbors. So you can convince yourself that at the end, if I take all of these interaction into account, the type of behavior that I'm gonna get is a threshold policy where an agent will find beneficial to select strategy 1 if enough of their neighbors have done so. So basically, at least tau fraction of his neighbors select strategy 1, then this agent will find more beneficial to select strategy 1, and the threshold depends on the specific payoff parameters. And again, these are just two very simple examples, but I hope that already they can give you a sense that how like the underlying network actually affects the behavior of people. And so indeed, this is kind of the general question that people have been studying in this literature, try to connect network structure to equilibrium outcome. So for example, a very fundamental question that you can ask is, well, how does the position that this agent has on the network is gonna influence the individual play? So coming back to the simple linear quadratic example, this was studied in this fundamental paper, seminal paper by Ballester et al. So remember, in that case, the cost function is linear quadratic, very simple. And if you fix the effect of other and you ask what's the best strategy of an agent, you really need to just simply minimize this function with respect to xi. So you'll find the solution is this simple expression here. And then if you put this in vector form, you get that at equilibrium, you need to verify some fixed point equation of this form here. And expressing x bar, you get an explicit formulation for what the Nash equilibrium is as a function of the network. And in fact, I mean, the details here are not so important, but what I find that's really interesting here is that you have a clear connection between equilibrium outcome and network in the sense of centrality measure of an agent. So what this is just like how central an agent has in terms of Bonachik centrality, which is a measure of incoming paths. And so this was a first example where there's really a clear connection between network and outcome. And then the literature has studied this problem for much more complicated setting where you don't have linear quadratic structure, but you maintain strategic complements or substitute structure, or more recently when you look into more complex setting with mixed interaction using the theory of variational inequalities. And even more interesting than that, I think like what people have been looked at is how do we actually exploit this information if we then want to make intervention on the system? So already in this 2006 paper, what they looked there in the context of crime application was, well, if I can remove one agent from my network, which one should I remove to decrease the activity level the most? And again, that they show that this is tied to some centrality measure. But then similar question can be applied actually to many settings. So you can ask question about optimal pricing from a monopolist for a product subject to network externalities. You can ask question about budget allocation for maximizing welfare, as I mentioned at the beginning of this talk, or you can ask question about optimal seeding in these coordination games. And one thing that I want to stress, however, is that in all these type of works that I mentioned here, in order to implement this intervention, of course, the central planner needs to know the underlying network information, right? What I've convinced you so far is that we have this connection between equilibrium outcome and network. In order for us to plan this intervention, we need to know the network. And this is really the key point or motivation for my work and my research in the last couple of years. And really, this comes from the observation that when we go to application where we have very large networks, actually two problems emerge with this approach that I've just described. So the first problem is that collecting exact network information may become extremely costly, or in some cases not at all be possible due to privacy constraints. And then the second main problem is that even if you had exact network information, some of the problems that I mentioned before are NP hard. So when you scale up your population, you make it really large, the computing the optimal intervention may become computationally intractable. So really what my research has been focused on is, can we still regulate strategic behavior when we are in this large network setting, and therefore we need to account for these problematics? And really the key observation in order to answer this question is that while it's true that in many settings the central planner doesn't have exact network information, it may still have some probabilistic description of how agents interact, which can be used to infer what is known as a stochastic network formation model. So basically some rule that describes how agents are interacting. And just to kind of show you why this could be interesting, what you see here is an example where a central planner doesn't know the exact network of interaction, but actually knows that there are two community of agents, the red and the blue agents, and it knows what is the probability that I'm going to have a link between agents of different communities. And of course, this is a statistical description, right? This doesn't pinpoint an exact network, but it gives you some information about what's going on in this system. And in fact, you can actually sample different realized networks from this information. So what you see here are 3 different realizations. And what I plotted at the bottom is the equilibrium in a simple linear quadratic game, as I've described before, played over these networks. And now, of course, you see that the equilibrium outcome is different because, of course, it depends on the realized network. But at the same time, you see there are some commonalities. Like, for example, red agents here tend to exert less effort at equilibrium than blue agents. So this is kind of what motivated us into asking the question, well, how close are Nash equilibria when we look at behavior over different sample networks? And what I think is even more interesting is to let the population go to infinity, so increase the number of agents. And then if you repeat the same experiment, you see that this distinction between behavior of red and blue agents becomes sharper and sharper. So you can even start asking, well, what's going to happen in the limit? Will this converge to some deterministic profile? And if so, can I actually exploit this information to design some robust intervention based only on statistical information about the way agents are interacting? And so the key core of this talk, or what I'm going to present, is try to answer this question basically for a network model that is slightly more general than the linear quadratic model, and for a stochastic way of describing network that is more general than this simple 2 community model that I've used here for illustration purposes. And in fact, what I'm going to use as a stochastic network formation model for this talk is going to be the tool of graphons. Now, for those of you who have not seen before, a graphon is just a symmetric measurable function W that maps the 0-1 square interval into 0-1. And actually, there's 2 ways that you can think of graphon in relation to networks. So the first way that you can think of this is as a limit of sequence of graphs when you let the number of nodes goes to infinity. So in particular, when you do this, you see that in the limit, you have a continuum of agents that you can think map into the 0-1 interval. And so in that sense, the value W in position UV, you can think of it as the level of interaction between 2 infinitesimal agents in position U and V in your limit model. And this is the way they were initially introduced. But there is also a second way in which you can think about graphon, which is in terms of random graph models. And so the idea is that you can use a graphon to describe a probability distribution in the space of graphs, so that you can sample the random graph from any graphon of any desired size. And so, for example, if you want to create a graph with 5 agents, what you can do is that, well, first of all, you can assign to each one of your agents a label UI, which is simply randomly sampled from 0-1 uniformly at random. And then once you have those labeled, what you can do is you can connect any pair of agents with Bernoulli probability given from the graphon evaluated at the corresponding label. And then you see, if I repeat this for every pair of agents, I'll get 1 realization of a network of desired size. And this is actually a quite powerful way to generate random graph, because it generalizes, for example, Evdo-Shreni random graph, where you connect every agent with the same probability. That would just be a constant graphon, right? While you can also obtain stochastic block models, which are kind of a generalization of these two community models that I presented before, where you partition agents in different communities. That, again, you can get with a graphon, which is now piecewise constant, and every piece is going to correspond to different community. And the theory of graphon has been there for quite some years now. So it started in 2006 and it's been found application in many different areas. So really the contribution of what I'm going to talk about today is how we combine this idea of graphon theory together with game theory, again, to be able to say something about strategic behavior in random networks, basically. And so this is kind of the picture that I want you to have in mind. So from now on, I'm going to define a sample network game as a network game, exactly as I've described at the beginning of this talk, which is going to be played over a network sampled from some stochastic network formation model. And for this talk, this is going to be a graphon. And the key question that I want to try to address in this talk is whether we can actually design analysis and intervention just based on information of the stochastic network formation model, and then apply that to the realized network and understand what guarantees can we say for each realized network. So again, just to clarify, basically here I'm looking at a setting where single agents are playing the realized network. They have complete information, they play the exact Nash equilibrium as before. It's just the central planner that doesn't know the network and wants to use this stochastic information to design an intervention that hopefully will work no matter what the realized network. And so what I'm going to do in this talk, I'm going to try to answer this question. First, for a class of network games that are smooth and convex. And for that, I'm going to talk about graphon games. And then at the very end, quickly, I will give you a second application to the coordination games where we had discrete action set. And for that, I'm going to introduce the tools of Graphene Contagion. Okay, so if there's no question, if like the framework is clear, I can then move to the first part of the talk. Okay, so here again, what we're trying to do is look at smooth network games, and this is some work that I've done together with Azumano Staglar from MIT. And so what we're going to look at is the framework of network game, exactly as I've described before. The only thing that I'm going to assume on top of that are some regularity conditions. So I'm going to assume that my feasibility set is compact and convex, and then my cost function is strongly convex in own strategy, and the gradient is Lipschitz in local aggregate. And these are somehow some standard conditions that have been used to analyze like smooth games. And again, the main objective is going to be try to understand what can we say about Nash equilibrium when the graph is sampled from a graphon. And if you remember, again, my interest here is for large graphs. So what I'm going to do is I'm going to proceed in an approach where first I'm going to take the limit. So I'm going to try to understand what happens when I have an infinite population. And so to do that, I'm going to introduce this concept of graphon game, which is going to be describing interaction for a continuum of agents. And I'm going to define equilibrium in this setting and try to understand some properties of the equilibrium. And then in the second part, I'm going to try to relate this infinite graphon game to actually what I'm interested in, which are games played over real network, which are finite size, and I can see them as sampled from the underlying graphon model. And so what I'm going to try to convince is that this abstract graphon game equilibrium concept is actually a good approximation of equilibrium in any of these finite network game, as long as I have a sufficiently large population. And then finally, I'm going to try to argue how this analysis insight is going to be useful to design intervention in a computationally efficient way for large network based only on statistical information. Okay, so let me start with the first step. Again, here, you're going to see this is quite intuitive. So what I want to do is define an equivalent of a network game, which is a game for finite population, where I go to a continuum of agents, so for an infinite population. And so here, the difference is that I'm going to label my agents in the 0-1 interval, But exactly as before, each agent wants to select a strategy to minimize a certain cost function, which depend on its own strategy and some local aggregate. And really the only thing that's going to be different from the set of network game is how we compute this local aggregate. So remember, before that was the average of strategy of other agents with respect to the parameters coming from the graph. So since we now have an infinite population, I'm going to have to compute an integral using as parameter the parameter coming from the graph. And exactly as before, I can define a concept of equilibrium, again, as a profile, a strategy profile, where no agent has any interest in unilateral deviations. And the only thing that's going to be different is that this is now going to be a function instead of a vector, right? Before I had an agent and action for each agent. Now I have a continuum of agents, so the function is going to be, so the Nash equilibrium is going to be a function. Let me see, I see there's a question in the chat. It looks like XU is measurable. Is there any greater regularity involved? No, yeah, that's actually the only thing that we're gonna assume for XU. And then, I mean, there's gonna be regularity that comes in the Graphon, and I'm gonna define some of those things as we go along. Okay, so now that we put up the definition of Nash equilibrium, the first thing that you can ask is, well, this is a nice definition, but does it actually exist? So for these games, can we actually find such a Nash equilibrium? And if we can, is this unique? And the way I'm gonna answer this is, again, to try to tie this to the underlying interaction structure, which here is given by the Graphon. So remember, for network games, the interaction is given by the adjacency matrix of the network, which really you should see it as a linear operator that maps vectors into vectors. Now, the equivalent object in the infinite space is what is known as the Graphon operator, which again is just a linear integral operator that in this case is going to map functions to functions. But again, you can kind of talk about properties of this linear operator like spectrum, eigenvalues, and eigenfunctions. And what I'm going to try to do is convince you that we can use that to kind of answer something about the Nash equilibrium. And in fact, our main theorem in this aspect says that if this condition here holds, which is again a condition on the maximum eigenvalue of our Graphon operator, then we can guarantee that a Nash equilibrium exists and is unique. And the way we prove this result is actually quite intuitive. So the way we do this is by looking at what is the best response mapping in this space and showing that under this assumption here, this is a contraction. And so you can actually use Banach's point theorem to say that this best response mapping is going to be one unique fixed point. And actually, it's well known that fixed point of the best response mapping corresponds to Nash equilibrium. So this is how we actually answer this question. And just to look a little bit more about this condition that we found, if we go back to the linear quadratic case, this condition here really simplifies into asking that this speed effect parameter is not too large. And in fact, we should bound this by the maximum eigenvalue, which you should think of how much my network is amplifying basically effects. And this is kind of interesting for those of you who know network game, because it's very similar to the standard condition for network games, existence and uniqueness of equilibria. There, the only difference is going to be that you have maximum eigenvalue of the adjacency matrix instead of the Graphon. And then, if you remember, before I told you there's this nice connection in linear quadratic game between equilibrium and Banach's centrality. Turns out that you can actually do exactly the same for infinite population. You just need to define Banach's centrality for Graphons. Okay, so basically, what have we done so far? Sorry, there's another question. Let me do that before going on. Yes, so if the lambda max condition is violated, then yes, there are examples. I actually don't know an example about uniqueness where you lose, when you lose existence, but definitely there are examples where you may lose uniqueness. So in that case, it's multiple equilibrium might arise when you don't have this condition here. So I hope that answered that question. Okay, and I mean, existence, actually, let me say, like here I presented this main result, but existence is much easier to obtain. So you can actually use Schauder fixed point theorem instead of Banach and actually prove that existence is much easier as long as you have basically some continuity and regularity property for your cost function. So existence is typically very easy to obtain in this setting. We really needed this condition for uniqueness. Okay, so basically what I've done so far is I've described what happens for the infinite population level, right? So I've described this fictitious game where I have an infinite population, and I told you what equilibrium is in that infinite population setting. But of course, that's not what happened in reality, right? In reality, we always have finite population. So really what I'm interested in is understanding what happens when I sample a network, a finite network from my graphon, what happened to equilibrium in that case. And so the second main result that I'm going to tell you is that, well, this concept of graphon equilibrium that we introduced is useful because it is a good approximation of the equilibrium in any finite network when we have large populations. And so the main result, to be a little bit more precise in this setting, is that under some regularity condition of my graphon, what we can guarantee is that with high probability, we can bound the distance between the graphon equilibrium and the equilibrium in the sample network by some quantity that goes to 0 when the number of agents goes to infinity. And maybe one thing that you can ask here is, what exactly do I mean by this? Because I mentioned that in finite network, the equilibrium is a vector, while in a graphon is a function. So how do I even compare these two? And so in order to do that, our first result was to show that you can actually map any finite network game into an auxiliary graphon game, which is going to be played over a piecewise constant graphon, where every piece corresponds basically to one of your finite agents. And then by using this reformulation, you can then, instead of comparing equilibria of finite network with graphon equilibrium, just compare two graphon equilibrium, the one over the original graphon and the one over this auxiliary graphon. And so you're now in the space of function, and you see this comparison is in the L2 norm in that space of function. And so once you have that, our second main step was to show that there's some continuity of the equilibrium, so that you can actually bound the distance of the equilibrium of two graphon by the distance of the corresponding graphon operators. And then this distance here can be upper bounded by this quantity that goes to 0 as n goes to infinity. So
Francesca, there's one question, yeah.
Does this make X bar epsilon Nash for a finite game? Yes, so in some sort of sense, yes, that's kind of the type of result. Yes, it would need to be, again, to be specified a bit in the sense that, again, the X bar is a function, so you would need to say, how do I specify that into a vector to map it exactly back to an epsilon Nash, but you can do that. There's some formal way that we actually do in the paper, but yes, that's the kind of result that you can also get as a corollary of what I just said. And so again, the picture that I want to have you in mind is that basically in any finite network, I have some exact equilibrium for the finite network, which you can map into this piecewise constant version. And when you let n goes to infinity, this will converge basically to the graphon equilibrium, which is here, this curve in blue. So basically, the larger the population size, the better your graphon equilibrium is an approximation of the exact Nash equilibrium in the sample networks. And I see there's another question by Z. What is the graph topology that corresponds to this continuity? I mean, this is, again, done in operator in the graphon operator norm. So that's how we define convergence for like the graphons. And then if you instead look at this convergence here, this is convergent in L2 norm, right? We see this as L2 function, and what we are converging is in the L2 norm for these functions. I hope that answered. I'm sorry, it's a little bit difficult to answer, like make sure that I completely answer question just looking at the chat, but just feel free to like write again in the chat if something was not clear. Okay, so hopefully that's clear. So now the next step is, well, how do we use this analysis and this convergence result that we just derived in order to actually plan intervention? Because that's the end goal, right? We want to understand how can we intervene on this system. And to kind of give you a sense of that, I want to zoom in on a specific problem that's been discussed in this paper by Galeotti et al. which is in the setting of linear quadratic network game. So again, remember linear quadratic network game, this is the cost function of all agents. And the setting that they look at in that case is a setting where you have a central planner that can modify this parameter beta I, which is kind of part of the marginal return that depends only on agent I. So this is known as the standalone marginal return. And the central planner can modify this from beta I to some beta at I. And the question that they were looking in this paper is, well, say you have a limited budget, how should I split my budget between different agents to maximize the overall welfare, which actually in linear quadratic games is proportional to the norm of the equilibrium. So basically I want to just maximize the equilibrium norm based to the constraint that I have a finite budget. And now this is a well-defined problem, but you should see that this scales with the population size. So the more agents you have, the more decision variable you have in this problem, which means that computing the exact solution to this problem, which is what I call here the network optimal, becomes really challenging for networks with more than a few hundreds of agents. And so to kind of alleviate that, in that paper, they actually started looking at what are some properties that this solution has. And based on that, they actually suggest a network heuristic where you actually allocate your budget according to the dominant eigenvector. And not to go too much in the detail, but this should make sense because we are in a strategic complement way, and the dominant eigenvector is the one that's amplified the most by the network, right? So in some sense, it makes sense. And in this setting, you want to allocate your budget in a way that's amplified the most by the network. But beside this, I mean, one thing that I want to kind of stress is both computing the network optimal and the network heuristic require exact network data, right? If I want to solve this, I will need to know exactly how agents interact. So in the spirit of what I've discussed so far, what we ask is, well, what if I don't have this exact network data? I only have the statistical description. So in this case, I only know the graphon. What can I do in that case? And so what we came up is a strategy. Well, we first try to solve the same problem for the infinite population. So we define an optimization problem now in the graphon space, which is really just the equivalent of this maximization problem where we go to the infinite population. So we want to select the budget allocation, which is now going to be a function subject to some constraint to maximize, in this case, the graphon equilibrium norm. And note that the optimal solution here, again, is going to be a function. And say for a moment you can do this. I'm going to discuss in a moment whether this is an easy problem to solve or not. But say you can find the optimal solution, you will get a function that tells you what to do for infinite population. Now, of course, what you want to do is you want to implement this for finite population. So what we define is what we call the graphon optimal policy, where you look at your agent I in any of your realized network, and you allocate a budget proportional to this function here, evaluated at the label of this agent. So if you remember at the very beginning of the talk, I said the way we sample agent is by assigning a random label in 0, 1, and then connecting them. So here we're just saying, okay, let's assign a budget to this agent according to this optimal function for the infinite population evaluated at the corresponding label. And of course, you have some normalization to guarantee that you satisfy the budget. And so what we show is that because of our convergence analysis that I've discussed before, you can actually show that with high probability, this intervention here will become asymptotically optimal. So in fact, you can lower bound basically the distance from optimality by some quantity that goes to 0 when n goes to infinity. So there's another question. Can you do this if I give you the graph and not the labels? That's a more interesting question. I guess we haven't really looked into that. Maybe you can, my guess to do that is you can try to use the graph to kind of recover the label like a posteriori, like based on the number of connections, maybe you can get a sense of what the label of that agent was, and then you can apply this. But no, to be precise, so far we assume that you know the label. So that like you know the graphon and you know the label. And typically the reason behind that is labels are associated, if you think of in a stochastic block model, are associated to some feature of the agent. So this could be like, for example, race, age, gender, or some observable thing that you can actually know as a central planner. But definitely it's an interesting future direction to see what can we say when we don't know the labels. Okay, and so basically this is nice, right? So we have these asymptotic optimality type of guarantees, but again, if you remember, there was a big caveat at the beginning of all of this that says, well, if you can solve this problem. And of course, that's a caveat because this is an optimization problem in a function space. So in general, of course, it's not necessarily tractable. But what we were able to show is that if your graphon has some regularity condition, and in particular, we focus on finite rank, meaning that there is only a finite number of eigenvalues of your graphon operator that are different from 0, then in that case, you can actually recast this problem as a finite dimensional problem, which has actually dimension r+1, so the rank of your graphon. And the idea is that typically this rank dimension is much smaller than the number of agents, so this becomes a computationally more tractable problem. And really the idea behind this, I'm not going to go into the proof for time constraints, but really the idea is that you can reformulate your problem by using spectral theorem, by using as basis the eigenfunction of your graphon. And so with that, you can prove that the optimal intervention is going to be a linear combination of eigenfunction of your graphon, and you just really need to find the coefficient of this linear combination. And if you only have finite rank, you have a finite number of those coefficients that you need to find. Okay, so to put this in practice, basically what is kind of an example of a finite rank graphon is a generalization of this community model that I described before. So suppose that you have a network where you have agents divided in k communities, and like let Q HK be the connectivity among two different community H and K, and pi k the size of the community. Then you can get this type of random structure by a stochastic block model graphon that has this form here. And what we show is that this is indeed finite rank, and in fact it has rank as the number of communities, and you can even compute or map one-to-one the eigenfunctions of this graphon to the eigenvectors of this matrix Q pi, where Q is the matrix of connectivities and pi is the matrix of community size. So there is a nice way to kind of compute what the eigenfunctions are for the stochastic block model graphon. And one nice insight is that these are piecewise constant with respect to the communities. So coming back to the problem that I've discussed before, remember the optimal solution was a combination, a linear combination of the eigenfunctions. Since all eigenfunctions are piecewise constant, as a nice corollary, when we have stochastic block model graphon, the graphon intervention is also going to have this piecewise constant structure, which in practical terms means you're going to do the same intervention to each agent in the same community, which has some kind of fairness type connotation to it. Okay, so just to show you how this works in practice, what we did was to simulate 80 different networks from a stochastic block model with 4 communities, and these were the interconnection between the communities. And in each one of these network, agents are trying to minimize linear quadratic cost function, as we've seen before. And importantly, what we wanted to understand is this setting as well. What happens if the central planner actually doesn't know the parameter of the stochastic network model, and maybe doesn't know also some of the parameters of the cost function, like, for example, this peer effect parameter. And so in reality, what the central planner would need to do is infer this from some real data. And so we actually consider 2 different types of data for that. So the type of data that is typically considered is exact data. So what is here called the tailed relational data, where you just go to every agent and ask the exact identity of each of the neighbor, and you can use that to recover exactly the network of interaction. So that would be the traditional approach if you want, which of course is very expensive. So, and it also has some problems about privacy, because really here you're asking about exact identity. So to overcome these difficulties, what was suggested in this paper here was instead the use of aggregated relational data sets, where instead of going to every agent, you just go to a subset of the agents. And to those agents, you only ask aggregate level information. So in this example of the communities, for example, you may ask, well, how many neighbors do you have in each one of the community? But you don't need to know the exact identity. And so what was shown in this paper is that this, like collecting this type of data is significantly cheaper. Like it leads to kind of 80% cost reduction, for example, in the case of rural villages. So this may actually allow you to apply this type of procedure more broadly. And so what we wanted to understand is, well, can we use this ART data instead of exact data to plan intervention? And to make the story short is that, well, if you want to plan network optimal or network heuristic, then the answer is no, right? In that case, I discussed before, you really need the exact network data. So ARD is not rich enough to compute these type of interventions. On the other hand, what we show is that if you want to plan the Graphon optimal intervention, then you can actually do that with aggregated relational data set. And the idea is that this is rich enough to identify the parameter of the stochastic block model. You really need to compute the mean on sub-Bernoulli realizations. And you can actually also recover some of the parameter of the cost function by doing these square regressions. So overall, basically, this Graphon optimal intervention requires less data than the network optimal and network heuristic. And then as a final comparison, what about performances? So what we show here is like the improvement that you get by allocating the budget according to this different intervention with respect to simple homogeneous allocation. And of course, the best is when you do the network optimal intervention because it's tailored for the specific network. But you see that when you have large population size, that becomes computationally intractable. So the network heuristic instead is always tractable, but it requires exact network data, and performances actually degrade a lot here with population size, while instead the Graphon optimal intervention that we suggest based on aggregated data has very good performances even for large populations. Okay, so this was like the end of the first part of the talk. Is there any question? Otherwise, I'll quickly go through the second part. Okay, so for the second part, I'm going to talk about this work about Graphene Contagion, and this is something that I've done together with Salman Errol from CMU and Alex Teitelboim from Oxford University. And really here, the idea is to look at network games that have a finite number of strategies. And in particular, we're going to look at the generalization of this coordination game that I mentioned at the very beginning of this talk. So if you remember there, we had agents at this threshold policy where they would adopt if enough of their neighbors adopted or selected strategy 1. And so here we are considering a generalization where we actually allow this threshold to be different for different agents. And now for this type of games, what is actually very interesting to look at are the dynamics. So let me call C0n the set of initial adopters, so agent that selected 1 at time 0. And then let's allow agents to revise their strategy in time according to their best response. So in particular, agent I will adopt at time t+1 if, again, enough of his neighbor have done so at time t. So, and again, this is specific to the threshold of the agents. And the reason why I say that these dynamics are interesting is because they correspond to a very well-studied model of diffusion, which is the linear threshold model, as originally introduced by Granovetter. And that's been studied a lot, both for deterministic network, but actually also for random networks. And a very interesting question, and one can ask in this setting, which was first formulated in the seminal paper by Camp et al. In 2003, is, well, suppose that I can actually see the finite number of agents at the beginning, which agent should I select based on network interconnection to make sure that I will have maximum diffusion, so a maximum number of final adopters. And this is a problem that's NP-hard per se. So what was shown in this paper is that actually when the thresholds are uniform, selected uniform at random, then a greedy heuristic will work well for this problem. Now, to implement this greedy heuristic, however, central planner again needs full network information. It needs to be able to compute basically what's going to happen if I add each one by one a new agent to my seed set. And so what was suggested in this paper 2017 is actually how can we study a similar question where, however, the network is not deterministic, is not known to the central planner, but it's sampled from a configuration model. And what they did there was to kind of use some tree-like structure of configuration model to kind of boil down basically this analysis to a one-dimensional differential equation that would describe the total number of adopters and its evolution over time. And so what I'm going to say very quickly here is how can we address similar question now when the network is sampled from a graphon? And what I want to convince you is kind of that the mathematics is going to be slightly different with respect to what I presented before, but the general type of concept, the general approach is similar. And so what I think is that actually this approach can be then generalized to other type of processes as well. So I think there's like some interesting in the overall procedure. And so again, we're going to proceed in 3 steps. So first, we're going to define a contagion process, a diffusion process for the infinite population. Then I'm going to argue that this is informative of what happens to finite population if you have large enough number of agents. And then I'm going to kind of argue how can we exploit this analysis to propose new seeding policies. So again, first step is defining contagion for the infinite population. And so really here, the idea again is very similar to contagion over finite network. Here, I'm going to denote by C0 the subset of 0, 1 now, which are the initial adopters. And then I'm going to define this iterative process where an agent U will adopt at time t if enough of its neighbors adopted at the previous iteration. And so how do I quantify that in a Graphon model, where that's just going to be the integral of the indicator function of the set of adopters at time t-1 weighted by the parameters coming from the Graphon divided by the degree of this agent in the Graphon model. And again, I'm going to say that the agent adopted, this is greater than some specific threshold for an agent with label U. And so just to kind of clarify this in a very simple Graphon, which is constant. So again, this will generate Erdős-Rényi model with actually constant threshold. What this expression here that I just mentioned simplifies to is just asking whether the mass of adopter at time t-1 is greater or not than the threshold. And so here you see, like for this simple model, we get very sharp prediction in the limit. So if my seed set has a measure that's less than the threshold, then there's no further contagion, right? Nobody will adopt. And this is kind of what's shown in this plot. This is the seed size. This is the fraction of final adopters. For small seed size, nothing happened. The final adopter are just the seed set. And then there is kind of this threshold transition that if my seed set becomes now greater than the threshold, then immediately everybody will adopt. And again, why? Because here I've assumed basically there's homogeneity in this infinite population. So if one adopts, everybody adopts. So this is kind of a very sharp prediction of what the behavior is going to be for the infinite population. Again, what we want to know is, well, is this predictive of what happens for finite population? And so for that, we need some convergence type of result. And I don't have time to cover that in the details. So just very informally, let me say that, again, we can say that if we have a large enough network, then with high probability, we can recover what happens in the finite network by looking at the Graphene contagion process in the infinite population. And in particular, the type of result that we get is, well, if the label of my agent belongs to the set of final adopter in the infinite population, then this agent will adopt with high probability in the sample network, while if it belongs to the set of non-adopters in the infinite model, then with high probability will not adopt in the realized network. And again, this is very informal, like there's some details that go into that. It has to do what happens when actually one agent in the infinite population is exactly at the threshold. There's some gray region there where we cannot conclude what happened to those agents, but I'll refer you to kind of the paper for the details of that. And just as an illustration of what happens for the Erdős-Rényi model that I presented before, this is like the average number of adopters over 300 realization of random networks for increasing size. And you see that, again, the more, the higher the population, the more the prediction of the Graphon model is a good prediction of behavior in any one of these random networks. And then finally, in the last 3 minutes, let me tell you how can we use this for seeding. So again, the idea is that, well, we can first define a seeding problem for the infinite space. So here we want to select a subset of 0, 1 of a given size measure to maximize the measure of final adopters. again, this is a problem that it's an infinite dimensional problem, so this may be complicated to solve, but what we were able to show is that if you have a graphon with a stochastic block model with k communities, again, this can be like boiled down to a problem with in selecting k variables. And in particular, what these k variables are the measure of agents that you need to seed in each one of your community. So you just need to really decide what mass of agents do I need to seed in each one of my community, with the constraint that the mass of agents that you seed should be this required size rho. And this will be the solution for the infinite population problem. But then you can actually kind of define an heuristic from that when you go to finite size. And the heuristic that we define is, well, just randomly seed n times ci star of your agents in each one of the communities. So basically try to keep the proportion of agents that you seed according to this optimal solution for the infinite population. And so just to conclude, basically this is a plot of the performance. So what you see here is as a function of the population size, the fraction of final adopters here under this Graphon policy that I just described. And the solid line is the median, and the shaded area are the quantiles for like 300 different networks. And you see Graphon policy performs really well here. Like, so already for like less than 100 population size, we get everybody adopts. So this is clearly the best possible outcome. Instead, we show like for the same networks, if you apply this greedy policy that I mentioned at the beginning, or even worse, a random policy where you just seed at random, then the performance will degrade sharply with the increase of the population size. So again, the advantage of the Graphon heuristic is that, first of all, you don't need the exact network data to compute it. You just need the connectivity from the stochastic block model. And you can find the optimal weight, solving a problem in dimension k instead of dimension n, and typically number of communities is much smaller than number of agents. Okay, so with that, let me conclude. So again, what I presented here are basically two instances of this general approach, where you, instead of designing intervention on exact network data, you try to design intervention based on some statistical network model, and then try to argue some robustness guarantees or performances for large populations. And again, I mentioned these are just two examples. There's many other works in this framework that are really exciting. And this is a review paper that we did together with Azu on some of these aspects, if you're interested to learn more. Okay, so this is all I wanted to say. And if you have any question, please feel free to like unmute yourself and ask.
So please feel free to ask any questions, but thank you so much, Francesca, for a delightful and very clear talk. And so with that, I would just invite anybody who has a question to please speak up.
So what happens if I actually do have detailed information about a substantial part of the network, and the rest of the network I know only statistically?
That's a good question. I actually don't know. I mean, in some sense, one thing that I want to say is that what this kind of theory tells you is that in the limit of large population, it's actually not that important to know the details. So like the other way that you can see this result is that, well, if my population is large enough, I don't really care about all the details because I have this asymptotic that kicks in. So I think like in that sense, yeah, you may be able to do a little bit better because some part of the networks you know, but this is also a result that tells you that you're not going to be able to improve more than much if you have large population. But then, of course, there's also like, here's a little bit like, I kind of argue that a bit in the context of the application for the stochastic block model in the targeted intervention, but a big area of research is, well, how do you come up with a statistical model in the first place? So I guess an interesting question there would be like, well, if I know only parts of my network, can I kind of from those parts infer what the statistic of the entire network would be? Or like, how do I actually go into this first step of like inferring the statistical model in the first place? So again, for stochastic block model where you know the community of each agent, that's kind of simple, but for more general graphons, that's an open question, and that's a very interesting one.
I see. Thank you very much. Thank you for a wonderful talk.
Thank you.
Anyone else with a question pressing on their mind?
I think I just had a very basic question. Like, if I want to apply this method for some application in mind, is this going to be giving me some kind of a simulation result, or would I get some theoretical guarantees for how that application is going to be like? I mean, for applying the kind of seeding policy or changing some kind of a behavior, communal behavior.
Yeah, I think like, I mean, I will need to better understand exactly the specific application, but the hope is like, yes, this type of procedure basically is going to give you an alternative to procedure that you would normally do based on exact data. So if you don't have that exact data, the hope is that this will kind of give you another way to design intervention and some theoretical guarantees on how suboptimal you are if you do that instead of using exact data. So you can even start asking question, well, is it worth for me if I'm a company to acquire much more specific data that's probably very costly, and I actually can only improve by a little bit about my revenue? So you can start making trade-off. How much money do I actually want to invest in acquiring exact data? Is this worth or not? And this is kind of hopefully giving you some ideas in that direction.
Would it also tell me the size of the network in a pilot project? Like, what would be something which would be enough to kind of lead on to the analysis?
I mean, these are all bounds specific, right? It's not just an asymptotic result that, yes, it works for n large, but like we have bounds on what that n should be, especially in the first part. So yeah, I guess that would also give you some indication basically on how large your network should be, such that you can actually do that.
Okay, thanks a lot. Thank you so much.
Well, with that, I think I'll invite everyone to unmute and perhaps even turn on their video so that they can clap and thank our speaker for a delightful seminar this afternoon. And so thank you very much, Francesca.
Thank you for having me.